Today we're going to start off with a review question. When I say review question, boy, do I mean a review question. This question we talked about 2 years ago when y'all were freshmen during geometry. Please determine the next 4 digits in this particular series, where the series is B, which is equal to 2, -4, 6, -8. And then item number 2, I'm just going to talk about like what shape the rest of the class is going to be, since we're pretty close to the end of the year, and I want you all to have a clear layout in your mind in terms of what's left, what work is left, what exams are left, just because it's good to plan accordingly. Make sure that if you have any late work that you deal with it, get it in, or based on your test scores, if you want to try and get your grade up before the final quarter grade is assessed, that you know that there's very few opportunities left to do that. I just want to outline what those opportunities are. And then after that, we'll get into notes today. The notes will have 2 different parts, so I'll be talking for a while. We're going to talk about a chapter that I'm skipping, but since I'm skipping the chapter, I want to keep it real brief and just give you guys a flavor for what it is that we're going to jump over. And then we'll get into the new section of notes. Are there any questions on that stuff or on the test from yesterday? No, okay. Let me take attendance and then I'll take some suggestions about what the answer is to part 1. Okay. Let's go ahead and get started. So could I have a volunteer take a crack at what are the next 4 digits?
10, -12, 14, and -16.
Okay, yeah, so that's the correct answer. This one's pretty unambiguous just because there are 4 digits to start off with. So this is the answer. I hope y'all remember doing this or something very close to this back when we were in geometry. I think the section would have been called conjecture, where we look at some sort of list of numbers or maybe a physical object with geometric properties, and we try and make guesses about the pattern, right? So what's the pattern that we observed here that allowed us to write those next 4 digits? What pattern is being observed here through this series?
From 2 to -4, it's -6.
That is not the pattern that is being observed here. I mean, that's true, but that's not what carries through these digits.
No, for the positive numbers, it's adding by 4, and for the negative numbers, it's subtracting by 4.
I guess that's one way to put it. Could I have somebody else attempt to describe this pattern?
Is it like even numbers with every other being negative?
That's one way to put it. Yeah, so it's even numbers and then every other digit is negative, right? So let's go ahead and break that down. So I like the part where every other number is negative. That's something we can use. So every other digit is negative. And then what was that other part? It's what kind of numbers?
They're even.
They're all even, right? So let's ignore the part where that lead term is negative. How does one produce a series of all even numbers? You start with an even number, and then what do you do each step?
+2.
You're adding 2 each time so that you stay within the set of even numbers. So each time we are increasing, and I'll put it this way, the absolute value of b by 2. And so these are the two things that allow us to generate out the rest of this pattern. And this is a geometry type task to just be asked to do this. However, the thing that's going to make this a pre-calculus type task this chapter is the fact that I will need you to then write this out as a function. And here is probably the simplest way to state what is generating this. We could say that our sequence is b sub n, where n is the basically what number it is within the sequence. So this would be b1, b2, b3, b4, b5, b6, b7, b8, right? And as long as we can build in mathematical objects which behave according to these two patterns, and then correctly connect those two mathematical objects, we should be able to make an equation which would let us generate any of the b's in this entire sequence. So this first part is one that we're going to use a lot. Every other digit here is going to be negative. And the way that we're going to achieve this is by putting -1 to the n. Notice -1 to the n is going to flip back and forth as we increase n by steps of 1, right? Where if you do -1 to the 1, that'll give you -1, but -1 squared is going to give you +1. This object gives back a -1 every time n is odd, and it gives back a +1 every time n is even. However, this leads us to a problem right away. -1 squared, what would that give us? I'm sorry, -1 to the 1, because this first entry here would be our b1. So n would be 1. What's -1 to the 1?
-1.
Right, so this would make it so that the first digit was negative, and then the second digit was positive. That's easy to fix. All I have to do to shift it over is add 1 to it. So now when we plug in 1, 1 plus 1 is 2, and our first digit is positive. 2 plus 1 is 3, and our second digit is negative, etc., etc., etc. The next part, and I'm just going to color code that as yellow. So that's what gives this thing the property that every other value is negative, -1 raised to an exponent. And then the second part is increasing by 2 each step. That part's a lot easier. That's just going to be 2n. So that every time I increase n by 1, it's going to increase our final value by 2. And then the last thing that we need to do in order to build out this sequence building equation is to go ahead and look at what we get when we plug in n is equal to 1. So when we plug in 1, we get back +2. And then let's see if this does that. I plug in 1, I get 2. Okay, so the absolute value is correct. And then 2 plus 1 is 3, -1 to the 3. I'm sorry, -1 squared is +1. So this works all on its own. So as long as we can look at the two features of our pattern, build out a mathematical object for each of those features, and then correctly combine them, in this case by multiplication, this will generate the sequence for this list forever. The nice thing about it is, instead of like counting it out manually, if we wanted to know what the 10,000th entry was, all we would have to do is plug 10,000 into this equation, and it would tell us what that 10,000th entry was. Okay. Item number 2, just so everybody knows, here's what the rest of the class looks like. We just finished chapter 9, and we are about to skip chapter 10. We're going to start today off by talking a little bit about chapter 10, but of course that means that all of the stuff that I'm going to discuss for maybe the first 10 or 15 minutes of this lecture, once I move on from the warm-up, won't ever be tested on. The reason why I'm skipping it is it's a fairly important and interesting topic of math called conic sections. But for the most part, it's not really asked that much on anything that you are going to see in the near future. It very rarely occurs in calculus even, like it's not something that is very useful to be asked about. The only people out there who are going to need conic sections moving forward are physicists and mathematicians. Engineers don't even really need conic sections. So I want to talk a little bit about it today, just in big, broad conceptual strokes, like what you want to take away from it. And of course, if you found that you needed to use this stuff mathematically at some point in the future, it's a Wikipedia article away, right? And I am doing that because I want to move on to chapter 11, which is Introduction to Statistics, so baby statistics. And this is due to the fact that with the realignment of standards to Common Core, which we haven't really done, our school maintains mostly a traditional math sequence, like this thing where we do Algebra 1, Geometry, Algebra 2, Pre-Cal is a very traditional system. And nowadays, schools that have moved all the way over into Common Core do it differently with a series of classes, with a few included, called integrated math. And the main difference I found in the sequence is that the other classes that are replaced by various levels of integrated math are sacrificing some cut of the class in exchange to build statistics out piece by piece over the course of a few years. I just want to make sure that, like, when y'all move on to next year, you have some exposure to statistics, because some of y'all may end up taking it instead of calculus. And for those of you headed towards like the biological field, understanding statistics is probably the most important math for what you'll be doing. And I want to make sure that you guys have the like building blocks of it so that it's not such a challenge next year. Chapter 11 is going to be our final quiz and final test of the class. After that, there will be no other assessments. So be sure to, you know, keep that in mind as we get to those assessments, that these are your last 2 major grades for the quarter. And then after that, we have chapter 12, which is going to be Introduction to Calculus. And we're going to talk about one of the 3 pillars of calculus. Next year, y'all will see, either in college or in high school, that calculus is made of 3 topics. First, you are introduced to limits. Then limits are used to derive this second thing called derivatives. And then, depending on the way in which your class is taught, you can then show that there's this third idea called integrals, which can be built out of either the idea of derivatives or built from first principle on the idea of limits. So in our introduction to calculus that we're going to do at the end of the book, with whatever time we have left leading up to the final, we won't be talking about derivatives and we won't be talking about integrals, but I want to make sure that we get a chance to look at and try limits before you guys see it at the start of next school year, just because it'll make it that much easier, you know? And here we're going to focus really hard on the vocab. But for this last chapter, chapter 12, our little intro to calculus with limits, because this is outside of the like scope of pre-calculus, it's in the book, but it's not part of what I would consider to be pre-calculus. It's straight up calculus. This chapter will contain no test, especially since like by the time we're here, we'll be past the AP test. And I figure it'll be hard to keep everybody's attention on additional assessments. Also, let me just go ahead and I'll take it now so that I can clear time around it. What days are your guys' AP tests for this group?
I think 15, 18, and 20, I think.
Yeah, 20 or 21.
So what is it on 15?
US history, and then on the 18th it's environmental science,
Okay.
and then the last one is AP Lang, but I'm trying to figure out if it's on the 20th or the 21st.
Okay, figure that out and
I
then
think
let me
20th.
know.
It's the 20th.
Yeah.
Okay. Then let me go ahead and blast some days around this for your guys' benefit, because I don't want to pack anything in near those tests.
Yeah, I think
So 14, 18, and 20. So yeah, we'll have class today, tomorrow, all through the middle of next week, and then we'll probably knock out the mid-chapter quiz for what we're doing around the 11th or 12th, probably the 12th. And then to accommodate for your guys' AP tests, plus I'll be real with you, I have a final on the 13th, and then I have my comprehensive exam, I think that weekend on like the 16th or something horrible. Let's try and do this. So we'll have our mid-chapter quiz on the 12th. Yeah. Yeah, we'll have our quiz on the 12th, and then we'll continue as much as possible, but we won't meet on the 14th. We obviously won't meet on the 15th, and then the weekend is the 16th, 17th. We won't meet on the 18th. We also won't meet on the 19th, and then of course we won't meet on the 20th, and then we'll reconvene on the 21st with something light, and then we'll wrap up the parts of the chapter that we're going to deal with after the AP test.
Wait, do you know when the school year ends, or anyone?
Yeah, the academic calendar wraps up right after right at the top of June. Let me pull up my OWSs because they're pre-filled until the end of the year with the academic calendar stuff. So we might not actually get into that much intro to calculus stuff because there's quite a few sections in this chapter. The last day of normal school is Monday, the 1st of June. And then there's one day off to study, and then the finals go that week from Wednesday to Friday. So yeah, after the AP test, we'll have like a week and a half of school to wrap up the chapter.
Done.
And then it's all done. Okay, so let me go ahead and do this first part that I was talking about. Oh, sorry. So that's the schedule up until the end of the year. I just want y'all to like have that in your brain and know how to plan accordingly. Are there any questions on this stuff? There's only 2 assessments left. Keep that in mind. And then around AP tests, we'll take these days off so that y'all can focus on your tests. Okay, great. And then let me put all of chapter 10 into a nutshell in case it comes up in your future if you happen to go into physics or pure mathematics. If you choose to major in pure math, then I guarantee this stuff will come up and somebody more able than myself will teach it to you. So what we're skipping in chapter 10 is conic sections. And I'm just going to take all of these ideas and I'm going to put them in a nutshell. There exists this object called a double cone. And the general equation for the double cone is the following. Z squared is equal to ax squared plus by squared. Now you'll notice that this equation isn't just made of x and y, it's made of x, y, and z. So if you were to graph it, you would have to graph it in 3D space. This does not fit on the xy plane. And if you graph this, here's what you get. You are going to get a doubled cone. So where this is along the z-axis, so this axis that cuts it through the middle, up and down, that is z. And the deal with the double cone in 3D space is the fact that it actually relates a bunch of equations that appear to be different in unity with one another, because it turns out they are all objects which sit somewhere on the surface of the double cone, right? So just right off the top, you should know that like the size of the double cone, the angle that is made where the two sides meet is based on A and B. The closer they are to each other, the tighter this double cone is going to be. The more different they are, the wider apart they're going to be. But everything that I'm about to write from here still remains the same. The following objects, which seem different but are not, so the ellipse, the circle, both of those are the same equation. And y'all remember the project at the top of the year where we graph with equations, the equations for ellipses and circles? They kind of look similar. They both have an x squared and a y squared, and the only way in which they differ is by some constants. That's because they're both actually the same equation. And both of these are also in unity with the parabola and the hyperbola, which I'll talk about in a second. The deal with this is that all four of these functions, they sit down on a 2D plane because each one of these is just a different intersection of plane and double cone. And the same way that you solve out an equation to see where two functions cross each other by setting them equal, you would do the same thing here. The only thing is that the direction of the plane determines, right? You take the equation of a plane, you have it intersect with this equation for the double cone, and depending on the properties of that plane, it will then reproduce one of these four equations based on the properties of that plane. So if I cut it perfectly perpendicular to the z-axis, I think we can all imagine in our mind's eye that this would trace out a circle, right? If I laid down a flat surface that cut through the cone at any position, it would give us a perfect circle. And the further away out it is, then the bigger that circle would be. If I cut it at some angle, so like this, then this would trace out an ellipse. We would still get a round thingum, except it would be stretched along one axis as opposed to the other, right? Giving us that elliptical shape. Up next is the parabola, which I think is also a pretty interesting look. The way that you build a parabola here is we take a side length, which is going to be parallel to one side of our double cone, and we cut it in here so that it only intersects with the top half of this. And if I cut it along this plane and then we traced where it touched the double cone, it would give us back a parabola that goes up one side and down the other. And then finally, the thing that produces a hyperbola, which is the only one of these math objects that you haven't seen yet. That's what you get if you cut it along a plane, which is parallel to the z-axis. So from here, I go over, and then I cut it along this plane. And if I do that, our function will have two pieces, a parabola-looking shaped U, which goes up, and another parabola-shaped U, which goes down. So the thing that I'm doing here to produce these four different objects is number one for the ellipse, and I'm just going to color code this. So here my ellipse is blue. The thing that produces that ellipse is a plane, which is at an odd angle. That's the only one that's not really special here, right? So if it's just some weird angle, we get an ellipse. The thing that gives us back a circle is a plane which is perpendicular to the z-axis. The thing that gives us back a parabola, this guy right here, is a plane which is parallel to a side of the double cone, where this is that old geometry parallel line symbol. And then the thing that gives us a hyperbola is a plane which is parallel to the z-axis. And that's everything that you actually need to know about conic sections. All four of these functions appear different when we graph them, but all of them are actually from the same parent function. It's just a matter of exactly what surface you are tracing on that parent function. And this stuff probably won't be super useful to you unless you choose to major in math or physics. This stuff is everywhere in physics. All of these shapes are the pathways that gravity is allowed to force upon an object. Most orbits are elliptical, but depending on the size of the object you're orbiting around and the speed you're traveling at, you could get these other shapes as your orbits. You could get a perfectly circular orbit, or you could get a parabolic orbit where you approach the planet that you're orbiting around and get launched out. And just in case my pictures aren't the bestest, here's a quick look at a computer-generated one. I got my ellipse, I got my circle, my parabola, and then my hyperbola cuts through two halves of the cone. And then here's another look at a computer-generated image where the plane is actually in there, so that you can see how it is that that plane is cutting through the double cone, where the one on the left gives us a circle, then the parabola, then the ellipse, and then finally one that's parallel to the z-axis gives back a hyperbola. Are there any questions on that stuff? The chapter that we're skipping that I'll never test on. I just want to make sure that y'all hear this once.
We actually did this last year.
Oh, you did?
Yeah.
Yeah, so I guarantee that the questions that they ask you about it in this book would be trickier, but yeah, it's important that you have already gotten down these concepts. Or like I find a lot in Algebra 2, they give you the first three, but not the last one. They give you circle, parabola, ellipse, but they don't go over hyperbola. Did y'all go over hyperbola last year?
No, we did, yeah.
Yeah.
Oh, you did?
Mm-hmm.
Tight,
Yeah.
okay, cool. Sweet, then that's just a good review then. And then yeah, for most of you, this is the last time you will ever see this idea. So if you're not gonna major in math or physics, everybody say goodbye to the double cone. Anyway, today we're kicking off chapter 11, which is, like I said, final quiz and test opportunity of the year. And in chapter 11, we are going to talk about sequence, probability, and counting theory, which we all know how to count, and we've actually started off some of these ideas in algebra, so some of this stuff will be familiar to you. What this is actually all about is this is the introduction to statistics. So this is all stuff that you need in order to do college level statistics, but don't get it twisted, this is not statistics, simply because we don't actually talk about any applications of these mathematics in this section. We're not going to talk about sample sizes or confidence values or error margins or any of that stuff, but these are the pieces of vocabulary and the fundamental relationships that you are going to need in order to understand what those equations are talking about when you get to statistics. And today we're going to talk about our very first section, 11.1, sequence. So this is what item 1 today in the warm-up was all about. That was a sequence question. And I just wanted to show you all that to remind you that that was a type of question that we worked on in geometry. And when we did it in geometry, I only asked you to list out the subsequent digits, right, to make a conjecture about the patterns. But what we're going to be doing in this section in pre-calc is we are going to be codifying this information in a big way with vocabulary and formal definitions. So just to start it off, a sequence is simply a list of numbers tied to a sequential, hence the word sequence, tied to a sequential list of increasing and positive integers. And a sequence could be given just as the list of numbers itself, and then you're asked to find the pattern, or you could even be given an equation which generates that list of numbers. But I think it's really important to appreciate that sequences are different types of mathematical objects than you are used to for the following subtle detail. Let's say that I have a sequence, a sub n is equal to n plus 1, And I also have the function equation y is equal to 1x plus 1. Now, let's do a quick compare and contrast here between these two objects, because while they seem identical, the only difference would be like a change in variable. We have to respect this feature, the positive integers part of the notion of a sequence. So for a sub n, if I were to generate the sequence, this would tell us that, well, a is going to be equal to what? What's my first digit going to be?
1.
This won't generate 1. What happens when I plug in my first n?
I guess any given number plus 1. Oh, I'm not sure.
That is not what this is talking about. No. So here's the difference between a sequence and a function. I am going to start at n is equal to 1, and I'm going to count up through the positive integers. So here are the n's that I am allowed to plug in. N is equal to 1, n is equal to 2, n is equal to 3, n is equal to 4. So when I plug in that first n is equal to 1, 1 plus 1 is 2. So this is going to give me the answer 2, comma, 3, comma, 4, comma, 5, dot, 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 all the way down. However, if I were to go over here and I were to make some sort of x and y table, here are some differences right off the bat, x and y. I could plug in -3 because this thing here is a function, and it would give me back -2. I could plug in 0 and I could get back 1. I could even do something crazy. I could plug in 1/2 and I could get back 3/2. And now if I were to graph these two, I think it would drive even deeper at the difference between how sequences behave mathematically and how regular old functions behave mathematically. Let's say that I were to graph this, and this is going to be a sub n versus n, right? So all of the values that I get out versus what I plug in. And then over here, I want to graph x versus y. So all of the values that I can get out versus all of the values that I can put in. So here I'll have x and y. Let's graph this one first. This one is nice and easy. What shape is that graph going to be?
The line.
It's going to be a line. Its intercept is at 1. Its slope is 1. So from 1, I go up 1 over here to 2, 3. And then I can connect these two dots with a line. And this is my graph of the line. Y is equal to x plus 1. This graph is not the same. If this is indeed a sequence, what this is saying is that I plug in 1 and I get back 2. So there's a point. I plug in 2, I get back 3. So there's a point. I plug in 3 and I get back 4. And there is a point. And this is the complete graph of the sequence. What's the difference?
Well, in this case, aren't they the same line?
They are not the same line because this is the graph of the line y is equal to x plus 1, and this is the complete graph of the sequence. Compare and contrast. If you were to go anything past this, your answer would then be incorrect for the graph of this sequence. Can I get somebody to compare and contrast what is the same about these two, what is different about them?
Is it that the graph of y is equal to x plus 1 goes on forever?
So that is one important thing. This thing has a domain that goes from -infinity to infinity, unless we break it up with some sort of piecewise definition. What's this thing's domain?
Just positive infinity.
Where to positive infinity?
Oh, 0 to positive. Or no, 1. No.
So
Two
this
to
thing is on the
positive.
domain of 1 to positive infinity. But it's even more detailed than that. What other detail would you have to give about the domain? What x's am I plugging in? This is incomplete information about what x values I'm allowed to plug in. The first one I can plug in is 1, then it goes off to infinity, and I can plug in all of those other values. But there's some other detail about the x values I'm plugging in. I'm plugging in 1 and 2. Am I plugging in any of the numbers in between?
Oh, no.
No. This sequence does not exist off integer values. It does not exist at the half. So not only is the domain 1 to infinity, it is integers on 1 to infinity. Integers only on the gap from 1 to infinity. So while they do have the same values where you plug in an integer, right? So if I were to go over here to my line, they have the exact same value here, and at the next integer, and at the next integer, and at the next integer. These two things are not identical. These are not just the same mathematical object. And the reason for this, like I said, the place where we're headed with all of this is statistics. This is due to the fact that we typically use sequences to describe real objects or events. Sequences, that is. And for a lot of the cases in our typical scenarios in statistics, right? If you're just using statistics to calculate something about gambling, you might use one of these to generate what your chance of winning a slot machine is every single time you pull the lever. Can you pull the lever of a slot machine 2.5 times? Okay.
No, obviously not, no.
No, or if you're using statistics to talk about some sort of medical trial, can you have 3.5 patients? Like, you might be able to generate that number on some sort of weirdo average, but in terms of plugging in values, the numbers that you plug in to get answers in statistics, for most real life cases, you can only plug in integer values because you can only count whole numbered objects. And so we have a math object that does that. That object is called the mathematical sequence. Is this okay?
So, Mr. Robinson, for the sequence, it's not even a line. It's just given points on an axis.
Correct. If you were to connect these dots with some sort of line, it would cease to be a sequence. You would have made a mistake. Yeah.
Okay.
Okay. So, and this is going to be a thing that y'all don't super care for, but you should know that I'm going to be asking you to do that kind of problem that we did in the warm-up, where I ask you to look at a string of digits and then generate for me some sort of relationship or pattern or whatever. There isn't one hard and fast way to do that, right? Like it's not like algebra, where algebra has simple rules. It's looking for some type of pattern, but I can give you some advice, especially for the more complicated ones. So generating equations of sequences. Here's just some like pro tips for how to do this. Like we saw in the warm-up, we had a sign flip back and forth. So the flipping back and forth of a sign typically means that you have some sort of object in there, which is of the form -1 to the n, or -1 to the n plus 1, depending on where your odd number is, whether or not odd ends are negative or even ends are negative. But no matter what, if you are moving forward and the sign is flipping back and forth, positive, negative, positive, negative, positive, negative, this is the thingy that does that. Number 2, if you have some sort of constant increase, like you're increasing the same amount every single step, which is to say an arithmetic increase, is typically going to be that increase, which I'll call A. So let's say that it's increasing by A every turn. This is going to rely on the object A, n, so that every time you step forward n, you also increase or decrease by whatever amount A is. In our warm-up, that increase in the absolute value was 2, and so we knew that the equation had to include some type of 2n. The other type of increase where maybe we increase by the same multiplier every time, that would be considered a geometric increase. Again, this is vocab from geometry, because we talked about arithmetic sequences and geometric sequences in 2 different sections. So let's say that our series, I'm sorry, I keep mixing up the 2. Let's say our sequence multiplies by 3 every time. So we go 1, 3, 9, 27, etc., right? In that case, we're multiplying by the same digit every single step. And so we're actually taking that increase and we're raising it to the n power. So if our geometric increase, the multiplier that we're getting every time is b, that means that our sequence has some sort of b to the n built into it. Again, like I said, if you go 1, 3, 9, 27, that's 3 to the 0, 3 to the 1, 3 squared, 3 cubed. If you're multiplying by something every time, you're actually increasing the exponent on that multiplier. And the last thing is, last pro tip, if you have a fraction, look for patterns in numerators and denominators separately. And so, for example, let's say that we have the following for example, let's say that we have the following sequence generating term. So I have a sub n is going to be equal to -1 to the n times n plus 1 divided by 2 to the n. And all that we want to do with this information is we would like to generate the first 5 terms. This is to say that I want to take a sub n and I want to list out a1, a2, a3, a4, and a5. So let's go ahead and do this, yeah? So item number 1, a1. We plug in 1 and what do we get? -1 to the 1 is going to tell us that our first term here is positive or negative.
Negative.
Okay, and then 1 plus 1 is going to give us 2 in the numerator. And then down below, 2 to the 1 will give us back 2. Go ahead, go down the line and generate those other 4. Is that okay? How does that look?
Yep, looks good.
Okay. And so the reason why we do this is that the hard thing to do here would be to look at this list of digits and from this reverse engineer what's going on in the actual equation that generates it. However, let's just go ahead and identify what bits and pieces are here that would give that away. Negative, positive, negative, positive, negative. So we have that flipping back and forth, right? So we have flipping signs. That tells us that this piece has to be here, that there's some sort of -1 to an exponent. And then the next thing that we can notice is what is going on with our numerator. +1, +1, +1, +1, this absolute value. So up top, this is what we call an arithmetic gain. Arithmetic of +1. So that's what this n plus 1 is doing each time it is gaining 1. And then down below, what kind of gain is this?
A geometric.
This is a geometric increase where we are multiplying by 2 every time, which is how we know that's what the 2 to the n is doing in the denominator. Now, this would be a nightmare procedure if these fractions were simplified, right? If this first term was -1, and then this was 3/4, and then this was -1/2, and then this was simplified down to -3/16 or whatever, you'd be like, what gibberish am I looking at? Which is why normally when you're given some sort of fractional series, you should find that this is intentionally unsimplified. So when you guys look at the homework, if you see that they are giving you -2/2, they are not simplifying it down to -1 for a good reason. Is this okay? The last thing that I want to point out before we're done with the notes is that these types of sequences don't have to be generated formally this way. Sequences can also be generated recursively, so a recursive sequence. In general, in math, and more importantly in computer science when y'all get there next year, which most of you should have to take some kind of fundamental computer science course, recursion is the use of a rule which refers to itself. And for example, let's go ahead and say that I have the sequence generator b sub n is equal to 2 to the n, right? So this right here would be the standard way to notate the sequence. So this is the standard way of writing this. And if I listed out my sequence here, this would be b is equal to, well, 2 to the 1 is going to be 2, and then 4, and then 8, and then 16, and then 32, right? I can also define this exact same sequence recursively, depending on exactly what it is we're doing and why one of these forms may be better than the other. And here's the recursive way to write about it. And again, the thing that makes it recursive is the fact that it's going to refer to itself. The thing that we have to do when we write down the recursive form of a sequence is write down what the first term is, because the recursion rule may not tell us that. So I have to say explicitly, b1 is equal to the number 2. And then after that, all we have to do to generate the rest of the sequence is say what we're doing every single time we step forward. So when I go from here to here, what am I doing?
Times 2.
Times 2. So here's how we can write that recursively. We would say that b n plus 1, right? So I want to go forward one step. We're going to add 1 to n. When I step forward, b sub n plus 1, take the last b, which in this case is b sub n, right? So you calculate b3 based on b2. You calculate b4 based on b3. You calculate b101 based on b100 by multiplying by 2. And so these two ways of writing down this sequence are equivalent to each other. There's no difference in the list generated by these rule sets. It's just different ways of writing down the exact same information. And here's what I'm saying. Recursion is it refers to itself. This equation is referring to itself right here. And yeah, if we took these instructions and followed them, well, okay, b sub 1 is equal, I'm sorry, b, my first entry is equal to 2. Oh my God, my brain. B's first entry is equal to 2. And now if I want to generate the next b, this is telling me take the previous b, multiply by 2, which will give me 4. Now I want the next one. Take the previous b to get the next one, multiply by 2. Take the previous b, multiply by 2, etc., down the line. So these two, even though they are written in different ways, one is standard, one is recursive, they are mathematically equivalent. And that's all we have time for today. This is definitely enough information to get started on the homework. Like I said, a lot of this stuff is intuition, so it's hard to codify into hard and fast notes. But when we come in tomorrow, I'll have a few more like bullet points for y'all, really just trivia and vocab. And then we'll have the rest of the period to work on the homework assignment itself. So be sure to have your books handy tomorrow. Y'all have a nice day, and I'll see you on Friday.
See you, Mr. Rollins.